Diamonds are a clear symbol of wealth and a staple in the world of jewellery. But they also serve many industrial applications due to their unique properties. The first diamonds are believed to have been discovered in the mines of India around 300 BC, but have since been discovered across the world. In 1953, a new method of synthesizing diamonds was discovered, and since then, the traditional mining and the synthesizing have competed in this industry. However, before that, what is a diamond? I'm sure most people understand that diamonds are expensive, but chemically speaking, diamonds are a carbon-based material, just like coal or graphite. But if these materials are all made of carbon, how are they different? Well, diamonds have a highly ordered three-dimensional structure, where each carbon is bonded to 4 other carbon atoms. This is different from coal and graphite, because they are only bonded to 3 other carbon atoms in a very disordered manner. But due to this highly ordered three-dimensional structure, diamonds have incredible properties, such as a high melting point, hardness, and an insolubility in water, making them an ideal material for many applications.
With all these great properties, where do natural diamonds come from? Well, natural diamonds require very specific conditions that are not naturally found on the surface, but are found deep underground.
We are talking about 120 to 800 kilometers underground in the lysospheric and sub-lysospheric regions. Down here, the temperature is between 900 to 1400 degrees Celsius, which is enough for copper to melt, and the pressure is 6 gigapascals, which is 59,000 times stronger than the Earth's surface pressure. These temperatures cause carbon molecules such as carbon dioxide or methane to react with the mantle and form a diamond.
However, clearly we have a problem. These diamonds are still hundreds of kilometers underground, and the deepest mine is less than 4 kilometers deep. So how do we get the diamonds to the surface? One way is kimberlite pipes, which carry diamonds to the surface. Kimberlite pipes form when kimberlite magma and gases within it rise rapidly into the Earth's crust. Over many years, this creates a fracture that reaches the surface and explodes out. Then, the pipe containing magma hardens over time due to lower surface temperature, creating rock, which is mined by humans today.
However, natural diamond mining is imperfect. Like mining or extraction, it causes large land disturbances and pollutes the surrounding region. Diamonds are also water intensive due to turning kimberlite rock into slurry when separating rock from diamond, which, if undealt with, leaves the water polluted. Finally, natural diamonds are also called blood diamonds due to the poor conditions and child labour employed by some African mines.
With adequate technology and the understanding that diamonds are merely structures of carbon, we inevitably tried to replicate the natural diamond forming process ourselves. The most obvious approach was to put the carbon material under high pressures and temperatures to directly mimic the geological conditions under the Earth. It was quickly realized that the conditions were too optimistic to succeed, as the setup needed was simply way too much. Direct diamond shock conversion needs something crazy, like 12 gigapascals and 3,500 kelvins, since at a greater temperature, a greater pressure would be needed to support it. A neat solution is to combine the carbon with other materials to aid in forming the diamonds.
By far the most effective and practical mix is carbon and iron, where the molten iron keeps the carbon dissolved and acts as another point of initiation for diamonds to form. Despite the revolutionary efficiency this has, intense conditions are still needed. The first synthetic diamonds were made under conditions of 7.5 gigapascals and 1700 Kelvin in 1953, and they used an iron carbide mix. To reach these temperatures, many mechanical designs were tried and tested throughout the course of diamond synthesizing history. The belt apparatus, first used in 1954, held the central chamber in a carefully shaped gasket while conical pistons applied pressure. This was an improvement on previous designs that wore out the mechanical parts rapidly with such stress to get to high pressures. Another way that has been used is to enclose the sample in a sort of split sphere with 8 parts all interlocking together. multiple layers of anvils may be designed into the overall apparatus.
Diamonds formed synthetically have slight differences in structure than those that are naturally formed. In some cases, the synthetic process is tailored to produce specifically structured diamonds for a particular use. For example, diamond grit is rare to find naturally and is almost always produced synthetically. The size of the crystals can be controlled by the conditions of the process, such as leaving the sample in higher temperatures for a shorter period of time. These smaller diamonds are typically more economical to synthesize than larger diamonds, as those require significantly more effort and energy. The cost of strong machinery, as well as the energy supply required to maintain these growth conditions for an extended period of time, is much higher than rates for mining practices.
Despite all the improvements to synthesizing diamonds, high temperatures and pressures are still major requirements when it comes to diamonds made in the lab. Given the costs associated with this, trying to produce diamonds under much milder conditions is the next step in the innovation of synthetic diamonds. Inspired by the use of a liquid gallium catalyst to produce graphene from methane, researchers have turned to liquid metal catalysts to grow diamonds under manageable conditions, with the goal being to exploit the various interactions between metal surfaces and carbon during chemical vapor deposition.
A combination of molten gallium, iron, nickel, and silicon was used, over which flowed methane and hydrogen gas at a temperature close to 1200 degrees Celsius. The biggest advantage of this experiment was completed at just 1 atmosphere. The diamond is obtained in the form of a thin film, which the researchers claim can be transferred to any other substrate.
While the development is in its very, very early stages, there's a great deal of scope in exploring diamond synthesis using liquid metal catalysts. Further areas of exploration include different sources of carbon, so not methane, and other methods to introduce them, different liquid metals or metal mixtures, using a larger area or interface, and optimizing with temperature.
The structure of diamond is very organized, with each carbon bonded to 4 other carbons to form a carbon network. This is consistent and highly ordered structure gives diamond its crystal-like properties, such as being transparent, causing light to diffract, and having high material hardness. For carbon to form this highly ordered tetrahedral structure, immense pressure, temperature are required to push each carbon atom into position and to remove any other stray atoms like hydrogen and oxygen.
This naturally occurs in Earth's upper mantle, below 120 kilometers deep, where the temperature is upwards of 900 to 1400 degrees Celsius and the pressure is greater than that of 59,000 atmospheric surface pressures. The magma, now with diamonds throughout, is called kimberlite. This kimberlite rises through the Earth's crust due to the high pressure on its gases, carbon dioxide and water, before erupting through the surface.
Synthetic diamonds are made similarly to natural diamonds with high temperatures and pressures. The carbon is dissolved in molten iron to lower the extreme conditions needed for the reaction to occur. Several different machines have been developed to house this reaction, including the belt press and the split sphere press. While these machines can make big diamonds, they take a long time and lots of power. Small diamonds, however, are formed very quickly and don't need as much power. These small synthetic diamonds have slightly different properties than natural diamonds and are mostly used in industrial machinery, such as electronics, optics, and precision machinery.
More recently, newer methods for diamond synthesis are being developed, such as chemical vapor depositions over polymetallic alloys that require only atmospheric pressure. These new methods could make larger synthetic diamonds more cost-effective and open new uses for the gemstone.
For 2,000 years, diamonds have captivated humanity, symbolizing wealth, love, and royalty. Being found exclusively in rare kimberlite deposits, their supply has always been determined by how fast we can pull them out of the ground. But since the 1950s, we've been able to synthesize our own diamonds through creative technology. Who knows? Maybe one day your wedding ring will be synthetic.
Should we keep going? Is that too good?
Yeah, 2 is good.